we introduce a bunch of things in 1127, and then in 1128 we go back and we go into more depth with them. So this is one example. You were introduced to the concept of acids and bases in 1127, but now we're going to go into more depth on them. And we have not given up on equilibrium constants. So as a review, originally, acids and bases were determined by taste. The modern science says that's not a good thing, but we can still taste certain acids and bases. Things that taste sour, lemon juice, things like that, are acids. The term acid actually comes from the Latin word for sour. Things that taste bitter, like baking soda, or unsweetened coffee, unsweetened chocolate, are alkali. The term alkali comes, anytime you see a word that starts with AL, it tells you it came through the Arabic. Kali comes from India to start with. It translates to from the ashes, because the first time they found these alkali were in wood ashes. We now don't use the term alkali as much. We use the term base. That was brought in the 1700s because they were being used as the base for making salts. So we do have major taste buds that are designed to pick up certain specific chemicals. Sour picks up acids. Bitter picks up bases. Sweet picks up any of the sugar compounds. Are you Luke?
Yes.
She got it fixed from the other end. It's just, it would not let me log in at all.
Okay.
But
Do you want to set up a time to meet, maybe after your class or something?
Yeah.
We can check that out.
That'll work.
What time do you get done?
This is over at 10:30.
Okay, I can come back then and we can kind of...
Thank you so much. So the sugar, the ones with all those OHs and the hydrogen bonding, get picked up by our sweet taste buds, unless they get too large. Flour doesn't taste sweet to us simply because the molecule is too big to fit into our taste buds. And then we have salty. Salty is designed to pick up any ionic compound, but in particular, it picks up NaCl the best because it's the right size and it matches well. Now, they have said that there is a fifth taste bud, the umami one. I am not convinced that that's a taste bud. That's just me. I'm not a food scientist. But they say it picks up MSG, and I have a hard time believing that we would have a taste bud specifically for MSG because it's not something that was used worldwide. I do admit umami is a great texture, but I'm still going with 4 taste buds. But they all have a specific chemical that they are attracted to. So acids are sour, bases are bitter. But we don't want to keep tasting things to tell whether they're acids or bases, so we want to define them. And there are 3 definitions for acids and bases. Chronologically, we'll start with the earliest one. And that is the Arrhenius definition. We've seen Arrhenius before, a couple of weeks ago, on the Arrhenius equation. He also did this. So he came up with what we consider to be the first definition of what acids and bases are. To Arrhenius, an acid was anything that contained an H+. In particular, an H+ connected with either one of the halogens or with a polyatomic. There are other things H attacks to, like water, but we do not consider water an acid. But the other half of water, if I have H+ in water, the other half of water is OH-. So Arrhenius is going to define his base as that other half, the OH-. Sorry. I don't need them to call back. I got it all set. He said he would come in an hour. Okay, another bad joke. Put some OH- on it because we take our baseball literally. So examples of acids include the three with the halogens, hydroiodic, hydrobromic, hydrochloric. They're all commonly used. HCl probably the most common. You can pick that up at Home Depot or Lowe's or any of those places. We used to use it to maintain the pH for a swimming pool. It's good for cleaning metals, and it can be found in certain household cleaning products. Then we get some that are attached to polyatomics, sulfuric and nitric. They're both used as fertilizers, not around here, but I moved here from southern New Mexico, which has ground that is what they refer to as caliche. It's basically hard packed limestone, which is very basic. So they literally spray nitric acid all over the fields to fix the acid-base balance. Unfortunately, both sulfuric acid and nitric acid can be used as explosives. Sulfuric acid is also, it says dyes and glues, it's also used to make detergents. So these acids have a lot of uses. Some examples of bases: sodium hydroxide, which is Drano, potassium hydroxide, which is paint remover. But this is a pretty limited version of what acids and bases are, because your blood is slightly basic. But we don't want to use something like Drano to keep our blood basic. So we need to extend that definition of what a base is a little bit. And we introduce our most common definition, and that is the Bronsted-Lowry definition. Now, the Bronsted-Lowry definition is not going to change the definition of an acid, but it's going to clarify it a little bit. So a Bronsted acid is something that has an H+, but that H+ only exists when you put it into solution and the compound breaks apart. So it's not just that there's an H+ there, but that H+ can come off when you put it in solution. It is that H+ in solution that defines that being an acid. So it's still the H+, but we're clarifying that it has to be something that breaks off to produce something in solution. Now, if you think about what an H+ is, hydrogen is one proton plus one electron. Take off the electron, and it's a free-floating proton. So we can refer to an acid as a proton donor. It just gives up a proton that it can donate to something else. Exactly the same acids, no change in what our definition of acid is. But now we're going to expand our definition of a base to be not just OH-, but anything capable to attaching to that H+, or something that we refer to as a proton acceptor. So OH- works because OH- is negative, it's going to react with the positive H. But any other negative ion can also act as a base if it picks up an H+. But more importantly, things that have lone pairs of electrons can attach to that H+. That free-floating proton does not want to stay free-floating. It wants to attach to the first thing it can find. And the first thing it can find might be just water. Oxygen has lone pairs. That H+ will stick to the lone pairs in the water molecule. But more importantly, in our bodies, what it attaches itself to most is nitrogen, in particular ammonia-based compounds. So we not only have the OH-, but we're adding other negative ions, and we're adding anything with a lone pair of electrons, in particular that ammonia or an ammonia-based molecule. And now we've extended our list of bases to include ammonia. There are other things. If I look at these ions, H2CO3, carbonic acid. That is an acid. The CO3 minus 2 anion picks up 2 hydrogens. But it could also pick up 1 hydrogen and a sodium and become NaHCO3. Still basic because it's still got a hydrogen there. That's baking soda. Baking soda tastes bitter. It is basic. Our third definition we'll get more into at the end of chapter 17, and that is our Lewis acids and bases. We defined by Arrhenius H pluses and OH minus. When we get to Bronsted-Lowry, we're keeping our acid definition as being H plus, but now we're saying our bases include things with lone pairs. When we move on to Lewis acids and bases, we're going to keep that definition of the base, anything that can attach to an H plus, something with a lone pair of electrons. But now we're going to allow our acid to be anything that can pick up that lone pair of electrons. So we're going to look at some of those things, as I said, at the end of chapter 17. We're going to look at Lewis acids and bases. Now, as I said, we clarified the definition of the acid with the Bronsted-Lowry. Acids and bases only exist in solution. HCl by itself is a gas, doesn't exhibit acidic properties. NaOH by itself is a solid. It doesn't exhibit basic properties. These exist only when we place them in solution. So when we start doing K values here, all of our acids and bases are going to have an AQ after them. They're going to be aqueous, which means we can put them into the Kc equation. Okay, there is an exception. This guy, this is a really cool experiment. If you take ammonia, which is a gas naturally, and you take HCl, which is a gas naturally, and you take the 2 solutions of them. I have the base of ammonia, I have the acid of HCl, but they both release fumes. And if you put them close together, you see a white smoke because they're actually making a solid. They're making NH4Cl, ammonium chloride. This is an exception to the rule that they always have to be in solution. I can react NH3 and HCl gases. And they act like they're an acid and a base. Okay. So we're going to focus in this chapter on the Bronsted-Lowry definitions. Proton donor, proton acceptor. H plus and anything they can pick up an H plus. Now they do only exist in solution. So they do dissociate. They break up into their ions in aqueous solution. It's not an acid or a base if it doesn't dissociate. You have to have those H pluses in solution. So as we saw in the previous slide, HCl becomes H plus and Cl minus, NaOH becomes Na plus and OH minus. So acids dissociate to give H plus, always. That is our Bronsted-Lowry definition of an acid. So just remember, HCl aqueous is hydrochloric acid, but HCl gas is just plain old hydrogen chloride. I know I'm repeating myself, but it's important to understand this. The problem is, once HCl or any other acid dissociates, we've got that H plus there. And that H plus is a proton. It wants to latch onto something. So in water, H plus does not actually exist. I will write H plus all the time because I'm lazy, but in reality, it's H3O plus, the hydronium ion. That H plus immediately attaches itself to a water molecule. So this guy is a hydrogen ion. This guy is the hydronium ion. It is what actually exists in aqueous solution. Okay, now, acids and bases can be classified as strong or weak. Strong acids are things like HCl, H2SO4, HNO3, whereas vinegar is a weak acid. So what distinguishes strong from weak? Well, it's measured by the amount of dissociation. If the acid dissociates 100%, it is not a reversible reaction. We can't have a K value. We have nothing of the original molecule that we started with left. It is all H plus and some anion. So a strong acid dissociates 100%. So if it dissociates 100%, not a reversible reaction. We cannot do a K value with a strong acid. But if it's weak, it dissociates less than 100%. And it doesn't make any difference how close to 100% it is. If there is one molecule left undissociated, it is considered to be a weak acid. A lot of them dissociate at very small percentages. HF, hydrofluoric acid. Nasty, nasty stuff, but not because it's a strong acid, but because of that fluorine and the things that it does. HF dissociates less than 10%. So I can have a reversible reaction. We're going to focus on the weak ones in this chapter. So that is a reversible reaction. HF and in water makes H3O plus and F minus, but F minus can then react with the H3O plus and go back to the HF. So this is the list your book gives you of the 6 strong acids. There's actually another one that they don't include. The halogens, with the exception of fluorine, chlorine, bromine, and iodine. Astatine's a rare radioactive material, so we're ignoring that. But the lower halogens and 4 of the polyatomics. Sulfur, SO4, nitrogen, NO3, and 2 of the chlorine, ClO3 and ClO4. We'll see why these are the 4 polyatomics that are strong. There's a bunch of other polyatomics that are not strong, like the H2CO3 that I showed. We'll see why a little bit later in the chapter. So those are the only ones we're going to consider to be strong. They dissociate 100%. Everything else we'll consider to be weak, and we can do an equilibrium constant. So you can see, strong acid, no HCl left. Weak acid, it's mostly HF left, just a little bit of H3O plus and F minus. But just because it contains hydrogen does not mean it's an acid. Methane gas is not an acid. That doesn't dissociate. It doesn't even go into water. That's natural gas. It doesn't go into water. NH3, despite the fact that it has H's on it, is a base, not an acid. Sugar is not an acid, even though it has all of those OHs. Even a simple alcohol, even though it looks like it has an H, that is not an acid, has an OH, isn't a base. So you have to be careful when you're looking at things that are acidic. It is just hydrogen with some of the halogens, hydrogen with polyatomics, and a few other things, like we can say sulfur creates an acidic compound, though it's not a very good one. Other than that, everything else is either not an acid or base at all, or a base. So to distinguish which ones are acids, that is acetic acid, that's vinegar. We write the H out front. By writing the H out front, it tells you that is what comes off. If it has more than one H, like sulfuric acid, H2SO4, both of the H's come off. So we write our acid specifically with the hydrogen out front so that we can see what it is that falls off. So doesn't make any difference how many H's I have, they all go to the front. Okay, so I did it again. I didn't put animations in. Okay, so it's asking me to compare HClO4 with HClO. HClO4 is one of the strong acids, so it's not a reversible reaction. Because it's not a reversible reaction, we will expect 100% dissociation. So HClO4 goes to H plus ClO4 minus. Now, because it associates 100%, if I have a 0.0015 molar solution of perchloric acid, I actually have 0.0015 molar H pluses in there. For a strong acid, the H plus concentration is the initial concentration of the acid. Now, HClO is a weak acid. So this becomes, I don't know why I put HClO3 in there. So that becomes a reversible reaction. So I need the double-headed arrow in there. And because of that, the amount of H plus I'm going to get out is much less than 0.0015. I don't know exactly how much less if I don't know what the percentage is of dissociation, but it will definitely be less than the original concentration. Now, bases dissociate to give OH minus. Even though our definition of a base is now expanded to things with lone pairs or other anions that can pick up an H+, our definition of a base is still going to be that it dissociates in water to give an OH-. Even if it doesn't have an OH- there, it's going to make an OH-. We'll see that in a minute. Bases can also be strong or weak. Our strong bases are the group 1A elements, lithium, sodium, potassium. We could go down to rubidium, cesium, francium, but again, they're less common. And then the bottom half of the group 2, calcium, strontium, and barium. Now, HF does not get in with a strong acid because it's too small, its bond is too tight, it doesn't break apart very well. The same thing is true of magnesium. Beryllium is not even a metal. Beryllium is a semi-metal, a metalloid, so it actually belongs over with boron. But magnesium is the first of your metals in that column. It's small, it makes tight bonds, so it doesn't break apart very well. So for both the halogens and the group 2A metals, the top ones don't count. But calcium, strontium, and barium all are strong. And all of these guys are hydroxides. They all have OHs in them, and they dissociate 100%. For the most part, we consider our weak bases to be ammonia derivatives. Not all of them. I showed you HCO3, but we will focus on the weak bases that are ammonia derivatives. By ammonia derivatives, I simply mean take any of the H's off of ammonia and replace them with R. R is just carbon chains. Now, ammonia doesn't have an OH on it. But when you place it into water, it is strong enough to pull a hydrogen, an H+, off of the water and create an H4+, which leaves behind that OH-. So these weak bases that are not OHs still make OH in solution because they break apart water, take the H plus, and then leave the OH minus behind. The same thing would be true for the baking soda, HCO3 minus. It will pick up or lose an H plus in the water, and if it picks up that H plus, it's going to create an OH minus. So another example of one that's not an ammonia derivative would be the carbonate ion. CO3 minus 2 in water rips the water apart to give me HCO3 minus and an OH minus. Whether a base has an OH attached to it or not, it must produce an OH minus in solution. So again, strong base, no NaOH left. Weak base, it's still mostly NH3. So this is something, though, that doesn't occur in an acid, but we have to take into account in these strong bases. H2SO4. We still would say the H plus concentration is the same as the original material because H2SO4 would break down losing only one H. So if I went back to this slide and I had H2SO4 of 0.0015 molar, my reaction is H2SO4 goes to H plus plus HSO4 minus. So the concentration of H plus is still 0.0015 molar. The H's never come off more than one at a time. You only take the first H off of this strong acid. That is not true of a strong base. A strong base will lose both of its OHs at the same time. So the concentration of OH minus in KOH is 0.34, but in BaOH2, it's twice that. So for CaOH2, SrOH2, and BaOH2, the concentration of OH minuses will be twice the concentration of the original solution. Those are the only three exceptions to having to write a 2 in front of it. Okay, now, whenever an acid breaks apart, the half that is not H plus, if it is a reversible reaction and can go backwards, then the other half that's not the H plus is going to be a base because it's going to be able to react with the H plus. Likewise, again, if it's not a strong base, when a base picks up that hydrogen, the other half that it leaves behind is an acid. So acids turn into bases, bases turn into acids when we have a reversible reaction. These are referred to as conjugates. An acid plus a base makes a conjugate acid and a conjugate base. Now this shows an acid plus a base. It doesn't have to be an acid plus a base. It could be an acid plus water. So if I have, this is just my abbreviation for acetic acid, it's C2H3O2. When it breaks apart, it makes H plus and OAC minus. Actually, I should have a water in here because that makes H3O plus. So this is an acid, it makes a base. Because that's a reversible reaction, the acetate ion could react with the H3O plus and go back to the acid. The same thing is true for base plus water. If I take that CO3 minus 2 that I used, plus H2O, goes to HCO3 minus 1 plus OH minus. CO3 minus 2 is a base. It creates the acid HCO3 minus, which can then react with the OH minus and go back to CO3 minus 2. In reversible reactions, an acid makes a base makes an acid, and they can go back and forth between the two of them. So here's my acetic acid with water acting as a base. Water goes to the acid, H3O+, and acetic acid goes to the base, the acetate ion. So this is acetic acid. This is the acetate ion. And I have water and the hydronium ion. When NH3, ammonia has two M's, reacts with water, it creates an acid, the ammonium ion, and the OH minus, which can then go back again. So an acid went to a base, acetic acid went to the acetate ion, a base went to an acid, the ammonia went to the ammonium ion. Now this is not going to be true with something like HCl, because HCl is a non-reversible reaction. It's going to make H plus and Cl minus, it's never going to go backwards. So that only works for weak acids and bases. Now pure water is interesting, because pure water can react with itself. Pure water is amphoteric. An amphoteric is any material that can act as an acid or a base. Water is not the only one. The bicarbonate ion is amphoteric. It can pick up a hydrogen and make H2CO3. It can release a hydrogen and make CO3 minus. That's a very important amphoteric material because it's part of what maintains the pH balance, the acid-base balance in your blood. But we want to focus on water right now. So water is amphoteric. It can act as an acid or a base. I learned the word amphoteric. It can also be referred to as amphiprotic. Those two words mean exactly the same thing. I use amphoteric because it's what I learned in school. So if we go back to that slide, we see when water reacted with an acid, it acted like a base, and it picked up an H+. But when water reacted with a base, it acted like an acid and lost its H+. So depending on what we put water with, it acted as either an acid or a base. But it also does the same thing all by its little lonesome. We're going to talk about how water just makes acids and bases in itself. So classify each species as an acid or a base and identify the pairs. So in the first one, we can see H2O is losing its hydrogen, and SO4 minus 2 is picking up a hydrogen. So in that case, H2O is acting like an acid, and its conjugate base is OH minus. SO4 minus 2 is acting like a base and picking up the hydrogen HSO4 minus. Now, HSO4 is another one of those amphoteric materials. So I could do another reaction where I put HSO4 minus into water and let it pick up a hydrogen, or I can do what the second one does and let it lose the hydrogen. So now it's acting like an acid, which goes to the base, but now water is acting like a base and going to the acid. So water can be acid or base depending on what you put it with. Okay, I guess we'll get back to water. I thought it started here. Okay, it's important to understand this is a bad example because this is not a reversible reaction. If I make this, acetic acid instead. The conjugate is always weaker than what you started with. So acetic acid is a weak acid, but the acetate ion is an even weaker base. H3O plus is a weak acid. H2O is an even weaker base. So they don't have the same strength. The more it wants to go forward, the stronger the acid will be, and it will create a stronger acid on the other side. So a very strong acid will produce a very weak conjugate base. A strong acid, one of our 7 strong acids, will produce a 0 base. HCl goes to H plus and Cl minus. Cl minus is not a base at all because it won't go backwards. So the strength flips. So if HClO is a stronger acid than HBrO, and which is greater than HIO, then their conjugates will be having lost the H, and they will flip their strength. So IO minus will be greater than BRO minus, which will be greater than CLO minus. So the strongest of those acids becomes the weakest of those conjugates. Same thing is true for bases. That's dimethylamide versus ammonia. The addition of those CH3 groups, which are methyl groups, improve the alkalinity of the material. But when you create the conjugate, it's going to go backwards. And if I look at their actual conjugates, I'm adding a hydrogen to each one. And I'm reversing the order of the strength. So NH3 is the weakest of the bases, but NH4 plus is the strongest of the acids. Okay, so I told you we'd get back to water. Because water has the ability to act as either an acid or a base, it is amphoteric. Within pure water, some of the water molecules can act as an acid and some of them can act as a base. And I get within water a reversible reaction where 2 H2Os are going to H3O plus and OH minus. This is called the autoionization of water. So within a pure water system, I have some acid and some base. But they're exactly equal amounts because every time I make an H3O plus, I have to make an OH minus. So H3O plus and OH minus will always be present in equal amounts in pure water. So this equals that. So even without the presence of an acid or a base, I will find H3O plus and OH minus in water. Oops. And it will produce an equilibrium. It is a reversible reaction. So if it produces an equilibrium, it will have an equilibrium constant. I told you guys we weren't giving up on K's. So the equilibrium constant, there is no denominator here because the reactants were water, liquid water. Liquids aren't included in an equilibrium constant. So this is it's a Kc, which means it's based on concentration. It's Kw, the equilibrium concentration for water. It's equal to the H3O plus times the OH minus, and the value is 1 times 10 to the minus 14. It's a pretty small value. We do not get a lot of H3O pluses and OH minuses in pure water. It's a very small K. Kw, when you get to your next test, next week, will be on your exam, on your equation sheet. You don't need to memorize this number. So if we do an equilibrium constant icebox, we don't have a first column. All we have is the H plus and the OH minus. So we have no original concentration at all, we just have products. So 1 times 10 to the minus 14 is equal to x squared, or x is equal to 1 times 10 to the minus 7 molar. So there are not a lot of H3O pluses or OH minuses in pure water, but there are some. Scrabble. What does HOH spell? Water. So H plus, OH minus, they have to be equal in pure water. They don't have to be equal in any other solution, but in pure water, they have to be equal. They are both equal to 1 times 10 to the minus 7. But that does depend on temperature. When we talk about 1 times 10 to the minus 14, we are talking about our standard temperature, which is 25 degrees Celsius. You can see, as it gets colder, it doesn't react as well. If when it gets colder, it doesn't react as well, this must be an endothermic reaction. So as I add heat, my K value gets larger and larger. I'm getting more and more H plus and OH minus. So at the boiling point, I've gone from 1 times 10 to the minus 14 to 5.4 times 10 to the minus 13. So I've gone up by a factor of about 50. Whereas going from 25 down to 0, I've gone down by about a factor of 10. So now, when we define acids and bases, we're going to define them according to what is the balance of the H3O plus and the OH minus. We know that acids have H pluses, but there's already some OH minuses in there from water. We want to know that in an acid, we have more H plus than we have OH minus. In a base, we want to know that we have more OH minus than we have H plus. Pure water is considered to be neutral. The H3O plus equals the OH minus. But the addition of an acid increases the H3O plus. The addition of a base increases the OH minus. So in an acid solution, the concentration of H plus is greater than OH minus. We just saw that on the previous slide, which means it has to be greater than 1 times 10 to the minus 7. So we can now put a number to what is an acid. An acid is anything where the H plus concentration is greater than 1 times 10 to the minus 7. And I know this is normally a time we take a break, but I got started 20 minutes late. So if you guys don't mind, I'm not going to take a break. On the other hand, in a base solution, the concentration of H plus becomes less than the concentration of OH minus, so our H plus is less than 1 times 10 to the minus 7. Now, I could say in a base that OH minus is greater than H plus, so it's greater than 1 times 10 to the minus 7, but I want to keep consistent. I'm going to keep this consistency by saying, what is the value of the H plus? It's 1 times 10 to the minus 7 in pure water. It's greater than that in an acid. It's less than that in a base. So, to repeat, acids are anything with an H plus greater than 1 times 10 to the minus 7. By the time I've said something 3 or 4 times, you can guarantee it's important. And bases are things where the H plus is less than 1 times 10 to the minus 7. Oh, okay. I could have taken a break. I didn't realize that this was such a short presentation. So what I want to do tomorrow is talk about the fact that I'm tired of saying 1 times 10 to the minus 7. We're going to find an easier way to talk about these concentrations. Now, I will admit, I I went on vacation over the weekend. I needed to get to the beach, so I was in Rhode Island for the weekend, which means I completely forgot about a bunch of things. So you have homework that was supposed to be due Wednesday that I haven't written yet. I don't know how the lab situation is. I have to check on that. So don't stress out about homework due Wednesday. If you get it done by Wednesday, that's fine. But make sure you get the pre-lab done. Pre-lab, somebody said I thought they would do at midnight. But pre-labs are due before you start labs on Wednesday morning. So your pre-labs are actually due by 9 o'clock that morning. So make sure you do it by Tuesday night. And I will get the homework up as soon as I get back to my desk. And I apologize. I worked through the homework problems with a student last week, the homework problems from chapter 14, didn't even start chapter 15. When I pick homework problems, I pick them according to the titles. I don't necessarily read what the problem is. And I think you guys will notice that. There was one that said, this reaction has an ISAB of 75 kilojoules per mole under normal conditions, but when you add a catalyst, it goes up to, the ISAB drops to 49 kilojoules per mole, something like that. It wants to know at what temperature the original would drop to the 49. I started to solve the problem and got myself confused. The idea was simply that you want them going at the same rate, so they both had to have equal rate constants. The Ks had to be equal, which meant that E sub A over RT1 had to equal E sub A over RT2, and you could solve for T2. But it took me a few minutes to figure that one out, because like I said, I started writing it down and said, well, K2 has to equal K1, and then I got myself totally confused. So I apologize, because like I said, all I read there in the thing was finding a second temperature. And I will tell you, anything that shows up with a brown banner across the top that says it came from a book, I apologize for all of those, because they come out of the Macquarie book, and I do not like Macquarie. He's used in the upper level PChem class, and I don't think he can do very well with writing PChem books, although there are people that disagree with me. I think he's awful at writing a Gen Chem book. So from now on, I think I have to do a better job of checking what the things are. The other thing that came up was, if any of you are having problems entering values into the labs, please let me know, because I found somebody who had entered stuff into the lab, and all of their numbers looked correct according to the data that they had collected, but LabFlow wanted twice that much. And I don't know how it would get twice that much from the data that they had. So if you're having any issue with entering data and LabFlow doesn't like it, please let me know. I will attempt to figure out what's going on. Okay, so it turns out I started 20 minutes late, and you're still going to get out 20 minutes early. I didn't realize that was such a short lecture, but that's okay, because bad morning, Monday morning. This is what I get for coming back from the beach. Should have just stayed at the beach, right? Okay, thanks, guys, for putting up with the crap that happened this morning. And tomorrow we'll look at other ways of finding H+ concentrations.